Let's take a look at question 7 in topic set 10 for Chem 11. This is a question about vapor pressure and calculating vapor pressure at different temperatures. A quick reminder, there's an equation that we discussed in class which is called the Clausius Clapeyron equation. And what this equation allows us to do is calculate vapor pressure at two different temperatures. The equation itself looks like this. ln of P1 over P2, where ln is natural log, is equal to negative of delta H of vap, which is the enthalpy of vaporization, divided by the gas constant times 1 over T1 minus 1 over T2, where T1 and T2 are the Kelvin temperatures. So T1 would be the temperature that gives rise to pressure 1 or P1, and T2 would be the temperature that gives rise to pressure 2. You can use T1 and T2 at any values. It doesn't have to be specifically that T1 is going to be smaller than T2 or vice versa. So you can really use it any way you want as long as T1 corresponds to the pressure of P1. So in this particular case, we're trying to solve for one of the temperatures, right? Because it tells us that the atmospheric pressure is 520. What's the boiling point of water? So we're trying to solve for temperature, which corresponds to boiling point. With this equation, as you see, we're going to need another data point. We're going to need another pressure temperature combination before we can solve this problem. So you can always use the normal boiling point, in this case of water, which is 100 degrees Celsius or 373 Kelvin. And we know that that boiling point occurs when pressure is equal to 1 atmosphere. So that will be your second data point that we can use to plug into the equation. So once we have that, we can do a little algebra first, and then we'll isolate one of the temperature variables, and then afterwards we can solve for it. So the first thing I'm going to do is just take all of these expression right here and bring it to the left side. So we'll have ln of P1 over P2 over negative delta H vap over R. That's now going to be equal to 1 over T1 minus 1 over T2. And then I will take this and bring it to the other side. And then I'm just going to swap the writing of the expression. So I have 1 over T1 equals to 1 over T2 plus ln of P1 over P2 over negative delta H vap over R. Okay, so hopefully you follow that algebraic step. Now what we can do is plug in some numbers. In this case, let's set T1 to be the boiling point of water at Breckenridge, which is the higher elevation. T2 in this case would be the boiling point at sea level, which is the normal boiling point, right? And that's 373 Kelvin. P1 in this case is the pressure at Breckenridge, which we were told is 520 torr. P2 is the pressure at sea level, which, as you know, is 1 atmosphere or 760 torr. I'm using torr here because the question gives us torr originally. The gas constant is this value for the joule per mole Kelvin unit, and then the enthalpy of vaporization is 40.7 kilojoules, or we can write it as 40,700 joules per mole. So now we can plug in all these numbers. 1 over T1 is equal to 1 over T2, where T2 is 373 Kelvin, plus ln of P1, which is 520, over 760. The torrs cancel away, and then over negative delta H vap, which is 4700 joules per mole, over R, which has that unit. And if you work out this expression, you should get 0.002758. The unit in this case is going to be inverse Kelvin. Now to find T1, you just need to take 1 over the number we just got, and that gives us 362.5 Kelvin, which if we convert to Celsius would be equal to 89.5 degrees Celsius. And we know this answer is correct because we know from experience that at higher elevation, boiling point decreases, so you're going to boil at a lower temperature, which is what we got.